last video of organic chemistry. So hopefully you watched that other video that I posted on separating petroleum compounds. It really does help to illustrate how they go about using the fractional distillation process. Fractional distillation is definitely a pretty important concept. If you were writing that diploma, you would see that there's usually at least one question using that fractional distillation tower. And that's obviously because this is something we do in our province, right? Like we collect crude oil and we have to be able to refine it, right? We have to be able to take that crude oil, which on its own really isn't that helpful of a compound, and we need to be able to separate all the different parts of it that are able to do helpful things for us, okay? So first step in any type of separating petroleum compounds is going to be that fractional distillation, right? So the idea behind fractional distillation is that we are going to heat the crude oil until it all turns into a gas. Then what happens is we're going to be able to separate the different components based off of their boiling points, right? Because what happens is they're going to start to condense at different temperatures. So when you looked at that video, you would have seen that they had that really big fractional distillation tower, right? Like it's a massive tower. So what happens in this, right, and you can kind of see this as we look at this picture, is at the bottom here, we put our crude oil in. We use steam to heat it to the point that it all evaporates. So now all the crude oil has turned into a gas. Okay, that gas is going to start to rise up this tower, right? And you would have seen in the video, there's kind of these like baffles, right? So it comes up because it's a gas, it's able to sneak underneath. And then here, the temperature is a little cooler than what it was down here. So we're going to start to see that some of our molecules are going to start to condense, right? So when you think back to when we did all our different functional groups, we talked about those boiling point and melting point trends within our families, right? So if you think about our alkanes and our alkenes, right, when we looked at those, we kind of had our little graph and we said that it looked like this, right? So that the more electrons we had by having more carbons, the higher that melting point and boiling point was going to be. So what we're going to find is that at the bottom of our tower, which is the hottest, this is where we are going to start to find our largest molecules. Okay, as we go up the tower, the temperature is going to continue to drop. So our biggest molecules are going to condense down here, but the smaller ones are still going to be a gas at that temperature. So they're going to continue to rise up the tower until eventually they reach whatever temperature they condense at. So we find the largest molecules at the bottom, and we find the smallest molecules are going to be up at the top of that tower, okay? So we're able to separate them, right? So if you look here on the side, you can see that we get our oil, our diesel fuels, right? These are 18 to 20 carbons are going to start to condense here, right? Where our temperature is anywhere between 230 and 426. And then as we go a little higher up, where the temperature is a little warmer, we get a few less carbons, right? Now we're at 15 to 18. We go higher up, now it's 12 to 50. Now it's 5 to 12, right? So the bigger molecules are going to condense at the bottom. And that's because those bigger molecules have higher boiling points, right? And that's because they have stronger LDFs. Okay, whereas our smaller ones up here, they have lower boiling points. And that's because they have weaker LDFs, right? So we're able to separate in a fractional distillation tower based off of those boiling points. And we have different boiling points because the strength of our intermolecular forces is different, right? The more electrons or the more carbons we have, the stronger that London dispersion force is and the higher that boiling point is going to be. So diploma-wise, if you had one, generally they're going to give you some molecules. Kind of a newer type of question they like to do is they're going to give you like 4 different compounds, and then they're going to kind of have this tower, and they're going to say this is spot 1, this is spot 2, spot 3, and spot 4. And they're going to ask you where would you collect each molecule. And it literally just comes down to like Let me figure out where's the biggest, work my way to the smallest. So the biggest is down here and the smallest is up at the top, okay? So in fractional distillation, we are separating based on boiling point, right? The other way to be able to separate things would be through solvent extraction, right? And if you think about earlier, when we talked about all the different families, we were talking about the use of water, hexane, and benzene. Those are kind of our three major solvents. And again, thinking back to Chem 20, we learned that like dissolves like. So water would be helpful for dissolving polar molecules. Well, if you think about polar molecules, those are only our small alcohols and our small carboxylic acids. So that's all that's going to dissolve in water. Then we talked about hexane. We said hexane was an aliphatic molecule. So that means other molecules that are aliphatic would dissolve into hexane. And then we talked about benzene, which was aromatic. So benzene is going to allow for me to separate aromatic compounds, right? So if I'm trying to refine crude oil, solvent extraction really isn't going to help me because the majority of molecules in crude oil are all going to be aliphatics. So they would all dissolve in hexane. So that really wouldn't help me actually be able to separate anything because they would just all be mixed together, which is why we generally use this fractional distillation. It lets us separate them based off of size. So the next process we generally do is what we call cracking and reforming. So in cracking and reforming, this is where we're going to take some of those products that we get from fractional distillation that maybe aren't really quite what we want, and we're going to turn them into what we want. So cracking basically means I'm going to take a larger molecule, I'm going to crack it apart into smaller molecules, right? Think of it as like you take a stick and you crack it in half, right? Whereas in reforming, I'm going to take some smaller things and I'm going to turn them into something larger that is actually what I want, okay? So there's different types of cracking. Some types of cracking will favor the production of certain types of molecules. So we can basically heat a hydrocarbon under pressure, and that's going to cause those carbon-carbon bonds to break, which is why it's called cracking. So one type of cracking is what we call steam cracking. So steam is basically really hot water. And when we steam crack something, we're just going to basically break it apart, right? So here's two examples of steam cracking. We've taken hexane, we've heated it, we put it under pressure, it's broken up into propane and propene. You will never be asked to write out a cracking reaction or a reforming reaction. Really, the biggest piece is for you to be able to be like, oh, okay, yeah, that's cracking because I took something big and I made it into something smaller. Or, oh, that's reforming because I took some little pieces and I turned that into something else, okay? So this is steam cracking. You can also do catalytic cracking, right? So this is where we would use a catalyst. The advantage to using the catalyst is that we find certain catalysts favor the production of certain things, right? So if I was trying to make diesel, or I was trying to make gasoline, or I was trying to make kerosene, there's a different catalyst that's going to favor those specific molecules when I break things apart. Because think about a stick, right? If you had 20 sticks and you went to crack all of them in half, some might be right down the middle, some might be to the side, right? You're not always going to get the exact same thing coming out at the end. So that catalyst is going to try to help favor it. Okay, the other thing we can do is add hydrogen, right? So if we do what's called hydrocracking, we're going to crack that molecule, but then what's going to happen is that hydrogen is going to be able to get rid of those double bonds, right? So if you go back to that previous slide, this had a double bond, this had a double bond, this had a double bond. But if we weren't looking for alkenes, rather we were looking for alkanes, I would do hydrocracking because then every time I made an alkene, that hydrogen would just automatically add into it and it would turn it into an alkane. Okay, so reforming, we're going to use heat, high pressure, catalysts, and we're going to join them together. There's alkylation, where we can join those short-chained alkanes. Sorry, this is like half off the screen, which is super helpful. Me zooming in didn't actually do what I wanted it to do. Let's see if I can fix this a bit. Getting closer. Apparently it's a massively wide slide. But really the biggest thing to recognize when it comes to reforming, again, we're not going to ask you to draw this out. It's just a matter of recognizing that we are going to take that larger or smaller molecule, and we're going to join them all together to be able to create something that's larger, looks a little more like what we want. Okay, apparently this is actually a pretty big slide. There we go. So reforming uses heat, high pressure, catalysts, converts those straight chained alkanes either into things that are branched because we add things to them, right? We're reforming, or maybe we can turn it into something that's cyclic or something that's aromatic. Alkylation, we use heat, sometimes catalysts, and we can use that to make special types of molecules, okay? So biggest thing out of this little video is really going to be that fractional distillation. Make sure that you understand that the point of it is to be able to separate a mixture of things based off of boiling points, and recognize that within that tower, the bigger molecules are at the bottom and the smaller molecules are at the top, okay? So that is the end of organic chemistry. Next unit we're going to do, I want to say, is going to be redox, so we'll be starting that in the following week, okay?